Alright, so here's lesson 5.1 for accelerated pre-calc, fundamental trig identities. So let's take a look at the trig identities that you guys need to remember. Alright, the fundamental trig identities here. The reciprocal identities, so we've been working with these, so I'm sure you guys are aware of them. Sine is equivalent to 1 over cosecant, which is its reciprocal. Cosine is equal to 1 over secant, which is its reciprocal, and so on. Cosecant is equal to 1 over sine, which is its reciprocal. Okay, and tangent we know is sine over cosine. Cotangent is cosine over sine. So we've been working with these, so I'm sure you're familiar with these. The Pythagorean identities, let me just review how these are generated. So we know that sine squared plus cosine squared basically comes from the unit circle, and the fact that if we have a unit circle, right, so radius here is 1. Let's say this angle here, we'll just call it u. Cosine represents the x-axis, y-axis is represented by sine. So if we do Pythagorean theorem here, we're going to end up with sine squared plus cosine squared is equal to 1. So that's where this basic Pythagorean identity comes from. And from this right here, we basically get the other two Pythagorean identities. Because if you just divide by cosine squared here, sine squared, divide everything by cosine squared. Sine squared over cosine squared, that's just going to give us tangent squared. Plus, that'll give us 1 is equal to 1 over cosine squared is basically going to be secant squared. Alright, so that's how we get this one right here, this Pythagorean identity. And the same thing over here, if you want to get this one, basically what you're doing is you're dividing everything by sine squared instead. If you divide everything by sine squared, sine squared over sine squared is going to give you 1. Over here we're going to get cotangent squared is equal to 1 over sine squared is going to give us cosecant squared. Alright, so that's how we get this Pythagorean identity over here. So if you know sine squared plus cosine squared over 1 is equal to 1, then you can divide this by either sine squared or cosine squared and get the other two Pythagorean identities. So you really don't need to memorize them as long as you understand how they are generated. Alright. What you need to be able to do is also manipulate these using algebra, right, to find their equivalents. For example, if I subtract sine squared on both sides, that would give me cosine squared u is equal to 1 minus sine squared u. Or if I subtract cosine squared on both sides, I would get sine squared u is equal to 1 minus cosine squared u. So just doing some basic algebra, right, subtracting terms on both sides, I get these equivalents also, right? And it's good to have all of these out when you guys are doing your homework, right, or write them out during the test, because we use these Pythagorean identities a lot. Okay, same thing over here. If I subtract tangent, 1 would be equal to secant squared u minus tangent squared u, or I could have tangent squared u is equal to secant squared u minus 1, right? So it's always good to generate all these Pythagorean identities and also manipulate them algebraically so that you can see all their equivalences. Cosecant squared minus 1, or we can have 1 is equal to cosecant squared u minus cotangent squared u. Okay. So these are the Pythagorean identities. Make sure that these values are always squared. Okay, if they're not squared, then they're not Pythagorean identities. Okay. So let me explain these cofunction identities and their ideas using a right triangle. So let's say we have a basic 3, 4, 5 right triangle. Let's say this angle right here is angle u. Well, then this angle right here would be 90 minus u, right? So this angle right here would be 90 minus u, right? Now, basically this says that, hey, if I take a sine of pi over 2, which is really 90 degrees, right? Right, so if I take the sine of this angle right here, well, the sine of this angle would be the opposite, which is 3 So the sine of 90 minus u, right, would be, is going to give us opposite over hypotenuse, 3 over 5, right? Well, they're saying this is equivalent to the cosine of our angle u. Well, the cosine of angle u right here, right? So here's cosine of angle u. I'll say this angle right here. Well, cosine is adjacent, which is 3 over hypotenuse, which is 5, right? So that's why these cofunction identities, that's why these are held to be true right here, right? So basically, if you have a right triangle, the sine of one angle is equivalent to the cosine of the other angle inside a right triangle. That's basically all this, that's basically all this says right here, okay? So if you have angle u, if you take 90 or pi over 2, right, in radian form, 90 minus u, you're just this just represents the other angle in the right triangle, okay? So just remember that sine pairs up with cosine for the cofunction identities, and tangent pairs up with cotangent, and secant pairs up with cosecant, okay? All right, the even and odd trig functions. First of all, cosine is considered an even function, okay? And these even and odd trig functions, these identities deal with when you have a negative angle, okay? So you notice there's a negative angle for all of these over here. So cosine is considered an even function, okay? And I'll explain why it's even in a moment. So since it's an even function, if you have the cosine of a negative angle, that is considered equivalent to the cosine of the positive of the angle, okay? And the same is true for the reciprocal function of cosine. Down here, sine and basically all the other trig functions are considered odd functions, okay? And what that means is the sine of a negative angle is equal to the negative of the sine function, okay? So basically what happens is, the way you want to think about it, the negative just gets pulled outside, right? And your answer is basically the opposite of the sine function. That's why it's the negative of the sine function, okay? And then over here, the same thing happens for, cosecant, cotangent, and tangent. You could think of it as, hey, this negative just gets pulled out, goes to the front, so you get negative of the tangent function, and etc. Right? So let me explain why these are even and odd. If you recall from our lesson before, earlier in the year, a function is even, all right, if you plug in negative x and you get back f of x. And a function is odd if you plug in negative x and you get back the negative of the function, the complete opposite, right? So that's why the sine and cosine functions are even and odd. Because right here, if you recall, an even function is symmetrical to the y-axis, and an odd function is symmetrical to the line y equals x, right? Or what they call the origin, the line y equals x right here, right? This is the line y equals x, so this is symmetrical to that line, right? So if you take a look at the graphs for cosine and sine, so if you take a look at cosine here, you notice that here's the y-axis. It's completely symmetrical on both sides right here. If you take this part, you flip it across the y-axis, you're going to get this right here. So since it's symmetrical to the y-axis, right, that's why cosine is considered an even function, okay, because it's symmetrical to the y-axis. Now, sine is symmetrical to the line y equals x, so I'll say this line right here. Right? So since it's symmetrical to the line y equals x, sine is symmetrical to the line y equals x, so sine is considered an odd function. Right? So that's the reason behind why these functions are even or odd. So I just remember what their graphs look like, and hey, are they symmetrical to the y-axis or not, or are they symmetrical to the line y equals x, right? So let's actually do some examples. So number one here, we've got all right. So we have this information here, and we've actually done something like this before in chapter 4. So it says tangent of some angle is greater than 0. That means tangent is positive. Well, tangent is only positive in quadrants 1 and 3. And secant, which is reciprocal with cosine, where is cosine negative? Well, cosine is negative in 2 and 3. So you know that the triangle has to be in quadrant, or it has to be in quadrant 3. So I'm draw a bigger one. So we know the triangle has to be in quadrant 3, right? So let's say here's angle U. So since secant is hypotenuse over adjacent, right? The hypotenuse is 3, and adjacent is negative 2. Alright, because x is negative here, right? So we need to do Pythagorean theorem and find this right here. So we do Pythagorean theorem, this is going to end up being negative rad 5, okay? So we need to find all the other trig ratios. We have sine u, then we have cosine u, tangent u, and we have cotangent u, and we have cosecant u. Alright, the sine of angle u is going to give us, sine is opposite right here over hypotenuse, so we get negative rad 5 over 3. Cosine, alright, is going to be adjacent, right, negative 2 over hypotenuse 3. Tangent is opposite, negative rad 5 over adjacent, negative 2. So we end up with positive rad 5 over 2, right? Because we know tangent is positive in the third quadrant. Cotangent, we could just flip this and then rationalize the denominator to rad 5 over 5. And then cosecant right here, we could just flip this, it'd be negative 3 rad 5 over 5, right, after we rationalize. So we've done this before, nothing new. So here are the answers here to that example. Let's take a look at this next example. So we're going to start simplifying trig expressions, and this is where things can get a little bit tough. So first thing right here is I see that, hey, I can pull out a GCF, sine of angle x. So I pulled out sine x, that's going to give me cosine squared x minus 1. Right, so all we're doing is we're just taking out a GCF like we did, you know, if they were like polynomials, stuff like that. So, and then over here, you can recognize that, hey, you can use the Pythagorean identities a lot. So since we have sine squared plus cosine squared is equal to 1, well, I know that sine squared is equal to 1 minus cosine squared. The problem is these are not the same right now. They're completely opposite. So since they're completely opposite, what I could do is I could pull out a negative 1. I'm going to factor out a negative 1 from here. So I'm going to factor out a negative 1. So I'll get negative 1 times sine x, or you can just put negative sine x, same thing. And then what happens is when I do that, it changes the signs of both of these because I took out a negative 1. So now I'll get negative cosine squared x plus 1. The reason why I take out the negative 1 is because now this is exactly the same as this, just written backwards, right? So now since these are equivalent, I can substitute this for sine squared, right? So I can plug this in here now. So I get negative sine x times sine squared x. And then when I multiply these, I get negative sine cubed x. And then that would be my answer. Okay? Alright, next example, let's talk about factoring. So when you're factoring these are pretty much the same way you would factor polynomials. So don't let the fact that they're trig expressions, you know, scare you. Like right here, this is really just a difference of squares. So this is going to give us secant theta plus 1 times secant theta minus 1. Okay? And then over here, this is the same thing as when you would factor 4x squared plus x minus 3. Alright? The only difference is instead of these x's now, they have these trig expressions. So don't let them, you know, scare you. You're still doing the same thing you did before when you were factoring. So if I factor this, I would end up with negative 12, positive 1. So what factors work? Looks like 4, negative 3, I divide by 4. This simplifies to 1 over 1. So I end up with, my factors are going to be, well, I need tangent squared, so it's going to be tangent times 4 tangent, right? Because basically you have the 1 right here, so tangent plus 1, and 4 tangent, and then minus 3, right? And you want to check tangent times 4 tangent gives you 4 tangent squared, okay? Multiply here, that's a negative. So if I multiply here, that gives me 4 tangent squared, and then you guys can put in the theta, right? So theta. And then we multiply here, we end up with negative 3 tangent theta. Multiply here, that's going to give us positive 4 tangent theta. Then multiply here, we get negative 3. So we get 4 tangent squared theta plus tangent theta minus 3. So it's really the same stuff we were doing before with polynomials. So don't let the fact that you have tangent, sine, or cosine, whatever here, scare you. The next example here, so we need to factor this one, but there's a problem. We have different trig ratios here, right? Now, whenever these trig ratios are, squared, what you want to do is you want to, always check your Pythagorean identities. So we know that cosecant squared is equal to 1 plus cotangent squared, okay? So since we know these are equivalent, what I'm going to do is I'm going to replace this right here with this. I'm going to substitute it in here. So then that's going to give me 1 plus cotangent squared x minus cotangent x minus 3. And then I can simplify like terms. These are like terms right here. So that's going to give me cotangent squared x minus cotangent x minus 2. So now we've got the same trig ratio, so now we can factor this. So basically, you guys can do the x if you want, but this one's pretty easy to factor. I already know it's going to be cotangent x times cotangent x. And then we have negative 2 and negative 1, so I know we're going to have negative 2 and a positive 1. So I multiply these right here. I check, I multiply this, I get this. If I multiply the 1 and the negative 2, I get the negative 2. So what you really need to check for is make sure you get the middle term. To check for the middle, you multiply the ends with the ones in the middle. So negative 2 cotangent, positive 1 cotangent, that leaves you with negative 1 cotangent. Okay? Alright, the next example here. So we need to simplify this. So the first thing I see is, hey, this cotangent, right? I'm going to change that to sine and cosine. So I have sine t plus, so cotangent, I know that's cosine t over sine t times cosine t over here, right? So these are multiplying, so I'm going to end up with sine t plus cosine squared t, because we're multiplying these, right, over what? Sine t. And then we need to get common denominator, right? So I'm multiplying by what? Sine t, sine t. So we're going to end up with sine squared t plus cosine squared t all over what? Sine t. So sine squared t plus cosine squared t, you have to recognize right here, hey, that's one of our Pythagorean theorems. That's really just 1. So we get over sine t, the reciprocal, alright, 1 over sine t, that's going to give us cosecant t as our answer. Okay? Alright, so this next example, we need to rewrite this so that it's not in fraction form. So we have 1 over 1 plus sine x. Well, we need to get rid of this denominator, obviously, if we can't have a fraction, right? So you should recognize this from something in the past. To get rid of this here, I'm going to have to multiply by the conjugate, which is 1 minus sine x, 1 minus sine x. So the top here, we're just going to end up with 1 times this is just going to give us 1 minus sine x on top. On the bottom, remember they're conjugates, you just multiply the first ones with the last ones. 1 minus sine squared x, right? So 1 minus sine squared, you guys should recognize, right, from our Pythagorean identities. Remember, we have sine squared plus cosine squared is equal to 1. Well, cosine squared is equal to 1 minus sine squared, right? And that's what we have right here. Okay, so we can replace this with cosine squared. So we're going to end up with 1 minus sine x over cosine squared x. And then what I'm going to do next is, well, I'm going to separate this. This can also be written as 1 over cosine squared x minus sine over cosine squared x, right? Basically, I'm just separating this, doing some algebra. Well, 1 over cosine squared x is going to give me, well, secant squared x, right? Over here, let me transition this. This right here, I'm going to rewrite it. Well, this is the same thing as sine over cosine times 1 over cosine, right? You can put the x right here. Because cosine times cosine gives me cosine squared, right? Well, what's sine over cosine? You can put the x right here. Sine over cosine gives us what? That's tangent x. And then 1 over cosine, well, what's the reciprocal of this? Well, that's just going to give me what? Secant x. Okay? And then we've written the problem now as a, it's not in fraction form. Alright, so you can just leave the answer like this. I mean, if you wanted to, you could factor out the secant x if you want, right? But you really don't have to, because we've accomplished what we wanted. It's basically write it so that it's not a fraction, right, anymore, right? Alright, so trig substitution. So it says use the substitution x equals 2 tangent theta, right? And then they just give you a domain here for theta, to write the square root of 4 plus x squared as a trig function of theta. Okay, so we have the square root of 4 plus, instead of x, we're replacing x with this right here, 2 tangent theta. 2 tangent theta. Okay, squared, because the x is being squared here. So we square this right here, we're going to end up with 4 plus 2 squared is 4 tangent squared theta. Okay, and then hey, we can factor out a GCF here. 4, we get 1 plus tangent squared theta. And then look at your list of Pythagorean identities. Okay, so we know that 1 plus tangent squared theta is equal to secant squared theta. So this right here, we can substitute it for this. So I'm going to take secant squared, replace it with this. So I'm going to end up with 4 times secant squared theta. Right? Now that these are multiplying, we can square root them. Okay, over here you can't square root this 4 right here and say the answer is 2, because this is one whole term, because this is being connected with this because of the plus, right? But now that these are multiplying with each other, we can square root the 4 and we get 2. The square root of secant squared is going to give us secant, right? So our answer is going to be 2 secant theta. Okay.